The next 5 questions are all ones in which you utilize the relationship that the delta H of a reaction is where you sum up all the heats of formation of the products, you sum up the heats of formation of the reactants, and you subtract the reactants from the products. So this particular one here, 2NH3 goes to N2 plus 3H2. Delta H is going to be the products, so that's heat of formation of N2, plus 3H2, so notice it's 3 times the heat of formation of H2, and the reactants is NH3, so it's 2 times the heat of formation of NH3, because we got that 2 there. There's the products in green minus the reactants in red. Now this one is nice and easy, because the heat of formation of N2, it's an element in its natural state, is 0. Heat of formation of H2, it's an element in its natural state, it's 0. Heat of formation of NH3 minus 46.1. So popping all that in, and we find heat of reaction 92.2. Important concepts brought out there, not just the overall concept. Heat of reaction is the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. But first of all, you have to use the coefficients from the equation. And of course, secondly, the heat of formation of elements is 0. Let's do one a little bit more complex. I've already put some pretty colors in there. So you can see I've got reactants, CH4 and 2Cl2. And for the product, CH2Cl2 and 2HCl. So let's pop those into the equation. So the heats of reaction, heat of formation of CH2Cl2, 2 times the heat of formation of HCl, minus the heat of formation of CH4. I haven't bothered to put in 2 times the heat of formation of Cl2 because it is an element in its natural state. Drop in the values that we get from what I was given. So CH2Cl heat of formation minus 95.4, heat of formation of HCl minus 92.3, heat of formation of CH4 is minus 74.6. And when I add all that together, then I get minus 205.4 kilojoules. Another one that is designed not just to illustrate the concepts that we're testing here, but also just emphasize the fact you have to be very, very careful when you're using numbers that you usually find in a big table of such numbers to use the right ones. So just to emphasize that here, you can see that I've got 1, 2, 3, 4, 5 substances in my equation, of which 1 is an element. So I won't even count that. So I've got 1, 2, 3, 4 substances, but I'm giving you stuff about 7 substances. You can see I've given you FeCl2 and FeCl3. Well, you only actually need FeCl3. I've given you HCl aqueous and HCl gas. Well, you only actually need HCl gas. So using some pretty little colors to highlight the idea, you can see that you have some redundant information given to you. That's fine. Life is all about redundant information. Don't expect to have only the data you need before you when you solve problems. Well, anyway, having got over that, the actual question itself is the same old thing. We're using the relationship that the heat of reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Pop in a very long expression the products and the reactants. Let's just double check ourselves, shall we? On our product side, we got 2 FeCl3. We got 4H2S. We have a Cl2, but we don't care in this case because it's an element. Heats of formation of elements are 0. And then on the product side, we have 2 FeS2 and we have 8 HCl. Now let's throw in the numbers for those. Just check again. FeCl3 is minus 399.5, H2S minus 20.6, FeS2 minus 178.2, and HCl gas is minus 92.3. Do the calculations. Important to note that you shouldn't just throw all this in a big chain on your calculator. I was so emphatic there I knocked my microphone. I wonder whether you can hear that or not. Anyway, so we add up all the products and it comes to minus 881.4. We add up all the reactants and it comes to minus 1094.8. Most common mistake people make on these problems is to leave out the coefficients. Second most common mistake is they do the calculation in such a way that they lose the fact that this is a minus of a minus. Okay, which is of course a plus. Very easy to lose negative signs in these calculations, so take your time and write it out in several steps. Anyway, here's what we're going to finish off with. Heat of reaction 213.4. Next one, I've already coloured it prettily for you. Same idea, same relationship. Pop in the products, being sure that we are counting our coefficients. So the products, H3PO4, 5HCl, H3PO4, 5HCl. Reactants, PCl5 and 4H2O, PCl5 and 4H2O. Drop in the values. H3PO4 minus 1284.4, HCl aqueous minus 167.1, there it is, PCl5 minus 443.5, and H2O, of which we have 4 of them, minus 285.8. Again, take your time doing the calculation, and you should get delta H minus 533.2 kilojoules. So, those last few questions have illustrated one big concept in delta H with some ancillary ones. Okay, the heat of a reaction is where you sum up the heats of formation of products minus the sum of the heats of formation of the reactants. And we've emphasized you have to use the coefficients because of course heats of formation are per mole. And we've also thrown in there bit by bit some various other tidbits. As the last question, we're going to combine our delta H with another concept completely far away from this module, that of gases. Anyway, already coloured it for you. Heat of formation of H2O is minus 242 kilojoules per mole. Always good to know. Calculate the heat change for the combustion of H2 gas, hydrogen gas. Well, H2 plus a half O2 goes to H2O is the combustion of H2 gas. Okay, so we could say the heat of reaction for the combustion of H2 gas is the heats of formation of the products minus the heats of formation of the reactants. Our product is water, for which we know minus 242 kilojoules per mole. Our reactants are both elements in a natural state, so therefore heat of formation 0. So therefore this heat of reaction, the heat of combustion of H2 is minus 242 kilojoules. But I wasn't asked for the heat of combustion of H2 because that would be for 1 mole of H2. I was asked for the heat of combustion of 11.2 litres of hydrogen gas. So this now brings in the gas module, which will actually be released in a couple of weeks if you're looking at this live, and the idea that for a gas, ideal gas, PV equals nRT. Well, continuing on, I told you the volume of hydrogen gas was 11.2 litres. There's T, 273 Kelvin. There's the pressure, 1 atmosphere pressure. There's the value of R, if you're using litres and atmospheres, which we are. So we pop all that in, and we find that 11.2 litres of hydrogen gas at 273 Kelvin and 1 atmosphere pressure is half a mole of hydrogen gas. Well, now it's straightforward. 1 mole is minus 242. Half a mole would be half of that, or minus 121 kilojoules.